Good morning, ladies and gentlemen. Actually, the time in Shanghai it's 3 p.m. afternoon already. Many thanks to Professor Virginia Paroikov for inviting me to attend this symposium. I'm Wei Liang from Drug Discovery and Design Center, Shanghai Institute of Material Medical, Chinese Academy of Sciences. Today I will talk about molecular dynamics simulation on the interactions between SARS coronavirus 2 spike protein and human ACE2, or between the spike protein and monoclonal antibodies. It's well known that it's well known that the spike protein are essential to viral infection. For instance, the first step of SARS-2 infection is the binding of its spike protein to ACE2. The spike on the surface of the virus particle is in a state of trimer. Here shows you the monomer. This domain that directly interact with ACE2 was called RBD domain, receptor binding domain. This the monomer has two different conformations called RBD down and RBD up conformations. I can't move this. What happened? Okay. Back to the early time in the year 2020, there are two experimental studies. One showed that the binding affinity between SARS-2 RBD and ACE2 are stronger than the binding affinity between SARS RBD and ACE2. Another experimental study shows that the binding of the full-length spike of SARS-2 to ACE2 is weaker than SARS. So these experimental results actually are contradictory to each other. So we want to know why. So in order to answer this question, we performed MD simulation. There are crystal structures available for the SARS RBD complexed with ACE2. So based on SARS crystal structure, we quickly constructed 3D models of the complexes of SARS-2, RBD, and ACE2. Then we performed MD simulation by using AMBER 16, and we ran 100 nanoseconds MD simulation and predicted the binding free energy by MMGBAC method. The result showed that the predicted binding free energy shows the binding between SARS-2 RBD and ACE2 is much stronger than SARS. So this result is in well agreement with the experimental results. And then we move on to the full-length spike protein system. Similar to the RBD domain, there are some crystal structures available for SARS spike protein complexed with ACE2. So based on this crystal structure, we constructed 3D models for the complexes of SARS-2 spike and ACE2. Then we run MD simulation and predicted the binding free energy. And we can see that each model the predicted binding free energy of Sars2 is stronger than Sars, but a different model has different value. So this calculated result demonstrated that the theoretical result is contradictory to experimental result. And meanwhile, we found that the different model has a different conformation, has different calculated data G. So this result shows that the conformation may be important to the binding free energy. So we want to have more conformations, and we want to sample the conformation on the transition pathway from RBD down conformation to up conformation by using a simulation method called NewMD, which we published in the year 2014. After the simulation, we obtained different conformations along the transition pathway from RBD down to up conformation. And then we define an angle called RBD angle, which actually is the angle DVV, this angle. And then we dock the HACE2 onto different conformation on the transition pathway. And we found that only when the conformation has the RBD angle larger than 52 degrees could the HACE2 be docked onto the conformation. We called this conformation HACE2 accessible, and this information HACE2 cannot be docked onto the conformation, so we call them HACE2 inaccessible conformation. So here shows you different RBD angle for the four model system I just showed you in last slide, and then we can see that as the RBD angle increased, the predicted binding energy, binding affinity become stronger and stronger. Nevertheless, the experimentally observed weak Sars2 spike HACE2 binding cannot be interpreted so far. So we think whether there is any other factor affecting the binding of spike to HACE2. So we think it might be the accessible conformation distribution. So in order to sample the conformation to understand the conformation distribution, we performed a large MD simulation by using this method called VSRMD, which we published in the year 2020. And we performed the simulation for Sars and Sars2 spikes with 48 replica. Each system was simulated for 100 milliseconds. Now here shows you the result. And this is the boundary between HACE2 accessible conformation and inaccessible conformation and the Sars system. And we found that the accessible conformations of Sars2 is only about 5%, but there are more than 22% of the conformation of Sars spike are accessible to HACE2. And meanwhile, we also found that the transition from inaccessible, this area, to accessible conformation of Sars2 has higher free energy barrier in comparison with Sars spike protein. And very impressively, the Sars spike has evenly distributed conformation space. In other words, the spike of Sars can bind to ACE2 by a conformation shift mechanism. While the Sars2, this protein, are mainly located in this area, inaccessible conformation space. So we can say that although the Sars2 spike RBD domain has stronger binding affinity to ACE2, the overall the full-length spike protein of Sars2 has much less accessible conformation and higher transition free energy barrier from inaccessible to accessible, making the Sars2 spike difficult to bind ACE2. So this might be at least one of the reasons why the full-length spike protein of Sars2 has a weaker binding affinity to ACE2 in comparison with the SARS. So in terms of the infectiousness of SARS2, human beings is quite lucky this time because it's a weaker bind to ACE2. So then we want to know why the SARS2 RBD bind to ACE2 stronger. Then we look into the interaction details between ACE2 and the RBD domain and of spike. And I show you all the key residues from the RBD with free energy contribution larger than 1 kcal per mole. Then we found some mutation, for instance, this N to Q, this L to RF. Some mutation enhanced the spike ACE2 binding. And then we think that the mutation may also be possible to affect the binding to the monoclonal antibodies of the spike protein. And we noticed a mutation called E484K mutation, which was reported in December of the year 2020. And the studies show that the new variant may have stronger binding to ACE2, means potential severe infectiousness. And also study shows the neutralization by some monoclonal antibodies against the variant was weakened, indicating potential immune evasion risk caused by this mutation. So we want to perform the simulation to study this observation. And again, we performed the MD simulation for the complex of spike protein and ACE2. And before and after mutation, we found that after the mutation, the spike protein has significantly stronger binding affinity to ACE2 in comparison with wild type, indicating the possible higher infectiousness of the new variant. And then we want to know whether also this mutation affected the binding to the monoclonal antibodies. We searched and found 25 antibodies complexed with RBD domain crystal structure. Then we constructed the mutated structure. And we performed the MD simulation and found that after the mutation, it becomes K, this gray box. Most of the systems, actually it's 88% of the systems showed decreased binding affinity to the mutated RBD. And only 4% showed increased binding affinity between the monoclonal antibody and spike protein. So it means the mutation may lead to a higher risk of immune evasion. And we look at the details of the contribution of this residue for before and after mutation to the binding free energy. We found some significant change took place. For instance, in this system, before mutation, there is a high, strong attraction between E484 and the antibody, because of the antibody, this area are positively charged. After the mutation, this E becomes K, then the K is positively charged. It becomes a repulsive interaction, lead to this very high repulsion. So this is the reason why the mutation may lead to some immune evasion risk. So we show the picture. We show the picture. The wild type spike protein attract the monoclonal antibody, and after the mutation, this attraction become repulsion. And then we want to study some other potential mutation with immune evasion risk. And we found that besides E484, this residue, there are additional 10 residues that are also important to binding monoclonal antibody. Among them, 6 are also important to binding HACE2. So if they are mutated, the mutant may have weaker binding affinity to HACE2. That means weaker infectiousness. But the rest of our residue, if the mutation takes place, it may enhance the binding between new variants and HACE2 and the new variants between the new variants and monoclonal antibody. That means higher infectiousness and higher immune evasion risk. And we also noticed a larger variant called Omicron, which was reported in the last November. And at that time, there is no any study reported. So we want to know whether this new mutation causes some severe infectiousness or immune evasion risk. Then we performed the MD simulation again. Here is the predicted binding free energy for the Omicron. Omicron has significantly weaker binding affinity to HACE2 in comparison with Delta. And it has a similar binding affinity to HACE2, similar as the wild type. In order to validate the calculation result, we carry out an experimental study. The experimental study also shows a similar result as the calculation result. And then
Dr.
we
Zhu, you have 2 minutes more. 2 minutes more.
Okay. Then we performed MD simulation for 5 monoclonal antibody systems, and we found that at least 3 monoclonal have a much weaker binding affinity to Omicron than in comparison with the binding affinity of wild type. So all the MD simulation revealed that the RBD domain of Omicron possesses much weaker binding affinity to HACE2 than the RBD domain of Delta. and also this Omicron variant has high risk of immune evasion. So here is a summary. With MD simulation, we found that the RBD of SARS-2 spike has stronger binding affinity to HACE2 than SARS, but the accessible conformation of SARS-2 spike is significantly less than SARS, which should be one of the reasons why SARS spike has weaker binding affinity to HACE2. And the variant with E484K mutation has weaker binding affinity to most monoclonal antibodies due to the weakened electrostatic interaction, which may lead to high immune evasion risk. And Omicron has lower binding affinity than Delta to HACE2, but it has greater potential risk of immune evasion to most monoclonal antibody. And so some publication shows it. So with these slides, I'd like to thank all my colleagues and my students, Professor Xu, Dr. Pang, Ms. Wu, Ms. Zhou, and Dr. Zhu, who performed the MD simulation, and Professor Gong and Ms. Mo. They carry out experimental study. With these slides, I'd like to thank you very much for your attention.
Thank you very much, Professor Chu, for this nice presentation. We have a number of questions in the chat box. The first one is from Vladimir Poroika. How great is the difference in confirmation in the RMSE terms? Dr. Chu?
Yes. Could you repeat the question?
How great is the difference in the confirmation in the RMSE terms?
In the what?
RMSE terms. Root mean square error.
RMS.
Root mean square error.
For
which system?
Actually, it's to your first slides when you say that confirmation plays essential rules in energy.
Which one? This?
Next.
Can you see my PowerPoint? Next.
Yes, fifth slide.
Fifth slide.
Yes. Different models have different confirmations.
Yes,
how big is the difference?
I can't remember RMSD, but the difference is very significant because the RBD angle is very different from each other, from 50 something degree to 80 something degree.
Okay, thank you.
Okay, my next question is from Vladimir Sulimov. How do you calculate ENP in AMBA? It is too small.
Calculate what?
ENP.
B and B.
Non-polar interactions on this slide.
This slide. On this slide?
Yes, this slide. Non-polar interaction, ENP.
Oh, this is just it's decomposition from the result. It's from MD directly from the MD simulation.
Yes. How physically do you calculate it? It is too small.
We use this protocol MMGBSA.
Yes. Thank you.
Okay. Thank you.
Okay. Next question is from Dimitri Shulga. How you constructed the complexes of RBD and MAB, or were they already available in PDB?
Yes, we at least we have we must have X-ray structure for one for either a SARS or SARS-2. Then we constructed another one. In most cases, we have the Sars crystal structure. Then we constructed the model for Sars2.
Okay. And another question from Vladimir Sulimov. How do you estimate accuracy of your MD calculation of delta G? Did you try
yes.
repeat some of the delta G calculation using some other force field like charm?
We repeated each simulation 3 times, and we reported the average and the error bar.
Last question about the force field. Did you change the force field?
We didn't. We tested maybe 2 or 3, but we didn't change frequently. After we determine, after we settle down the parameters, we didn't change because the system is similar to each other.
Thank you.
Okay, thank you. There is no other question in the chat box, but I can ask you another question. Many drugs or drug candidates have shown good binding affinity with different targets in silico experiment, but clinically many of them fail. So can you comment on this?
This is very complicated. I think it's strongly related to druggability of compound, small molecule. For especially the ADMET property. The in vitro activity does not mean good in vitro activity does not mean good in vivo activity, and a good in vivo activity does not mean good safety profile. So failure is frequently observed.
Yeah. Okay, thank you very much, Professor Zhu, for your presentation. Thank you very much.
Thank you.